The welding torch hisses in the darkness, metal on metal, and the man holding it knows he has maybe 8 hours to live. Captain Zatiev's engineer is sealing a crack in the primary coolant loop, the radioactive heart of a Soviet submarine, while extreme decay heat from the emergency shutdown continues to build 30 meters beneath the Atlantic. No one has ever attempted this repair. No one has survived the radiation levels in that compartment longer than 14 minutes. But here's what breaks the logic. The crew is improvising a solution no manual ever covered, jury-rigging a bypass system from the submarine's fresh water tanks. And every man selected for the welding rotation shares one specific detail in their service record that the captain wasn't cleared to know. 300 meters away, an American destroyer tracks them on passive sonar, listening to sounds that don't match any known Soviet submarine signature. Sounds that, according to the acoustic profile, shouldn't be possible from a vessel that's supposed to be operational. In 6 hours, K-19 will surface. In 7, the Americans will photograph something that will be classified for 41 years. But first, 7 more men have to enter that compartment. 1958. Soviet submariners receive orders that would have been impossible just months before. Hunt American carrier groups. Stay submerged for months. Patrol under the Arctic ice without ever surfacing for air. How? The Soviet Navy had just deployed its first nuclear-powered attack submarines, the November-class boats, with the Hotel-class ballistic missile submarines soon to follow. Each vessel was driven by 2 VMA pressurized water reactors, producing 70 megawatts of thermal energy. And here's what made them dangerous. These were not experimental prototypes. They were frontline warships. The reactor provided unlimited submerged endurance, eliminating the need to surface for air or battery charging. For the first time, a submarine could remain hidden for months at a stretch, keeping pace with surface fleets and remaining on station in hostile waters without resupply. NATO carrier groups now had a predator that could follow them anywhere, unseen, for as long as it took. Patrol cycles for these early boats typically ran around 60 days. 60 days submerged in the North Atlantic or beneath Arctic ice, maintaining readiness to launch R-13 ballistic missiles as strategic land targets. No port calls, minimal surface transits, no external support. The Hotel-class submarines carried 3 missile tubes. Each R-13 had a range of 600 kilometers and a thermonuclear warhead. The patrol mission required the crew to remain at their stations, the reactor to run continuously, and the boat to stay deep enough to avoid detection by NATO sonar nets strung across the Greenland-Iceland-UK gap. Though the R-13 system itself required the submarine to surface for missile launch. Crew berthing compartments sat directly adjacent to the reactor spaces. A single pressure hull bulkhead and a set of internal shielding panels separated the men who slept there from the reactor core. Officers bunked forward, enlisted men aft, but everyone aboard lived within a few meters of 140 megawatts of running reactors. There was no other way to arrange the interior. A submarine is a pressure vessel optimized for hydrodynamic efficiency and internal volume. Every cubic meter is accounted for. Weapons, missiles, ballast tanks, batteries, stores, and crew all compete for space, and the reactor compartment occupies the center of the hull because that is where the weight must sit for proper trim. Engineering watch sections typically rotated every 4 hours on Soviet submarines, though practices varied by vessel. Reactor compartment entry became necessary when equipment failures demanded manual intervention, valve adjustments, pump monitoring, emergency repairs that automated systems could no longer handle. On early Soviet boats plagued by faulty automation, a watchstander would unlock the watertight door, step through into the compartment, and complete his checks. Temperature, pressure, flow rate, radiation levels on the bulkhead monitor. Then he would exit, log the readings, and the next man would take over hours later. While Western submarines use shielding and remote monitoring to keep reactor compartments unmanned, some early Soviet designs required these dangerous entries. Many Soviet boats were equipped with dual reactors for redundancy, but shutting down the propulsion system at sea still meant losing the speed and maneuverability that kept the submarine alive. Captain's standing orders were explicit: maintain strategic patrol station and communication schedule regardless of mechanical casualties, short of total propulsion loss. If a pump failed, switch to the backup. If a steam leak developed, isolate the affected section and continue on reduced power. The mission came first. NATO surveillance aircraft patrolled overhead, destroyers worked the sonar nets, and any deviation from patrol routine risked detection or, worse, the assumption that the submarine had been compromised. Surfacing in enemy waters meant exposing the boat, the crew, the missiles, and the cipher materials to potential capture. That was unacceptable. The design bureaus made a choice early in the program. Reactor compartment lead shielding was reduced by roughly 40% below the initial specification. The reason was weight. A nuclear submarine must maintain neutral buoyancy and precise center of gravity for submerged maneuvering. Every kilogram of lead added to the shielding meant removing a kilogram of fuel, stores, weapons, or ballast capacity. The engineers calculated that the reduction would increase radiation exposure in adjoining spaces, but would not immediately incapacitate the crew. That judgment allowed the November and Hotel classes to meet their performance targets. It also meant the men who lived and worked next to the reactor would absorb far more radiation than anyone acknowledged. Sailors who served on these vessels reportedly used grimmer nicknames, comparing their boats to floating disasters, though the specific terms varied by crew and era. Adjoining berthing spaces and the forward control room reportedly measured 8 to 12 milliroentgens per hour during normal reactor operation, 10 times the safe continuous exposure threshold. A man sleeping in his bunk accumulated more radiation in one night than a civilian worker was permitted in an entire year. During patrols plagued by reactor leaks, cumulative doses could reach levels high enough to cause chronic radiation sickness, with blood changes, immune suppression, and elevated cancer risk. But the patrol had to continue, so the exposure continued, and no one outside the submarine knew the numbers, because no one inside the submarine could measure them. The Soviet Navy did not issue personal dosimeters to submarine crews until 1963. Commanding officers had no instrument capability to measure radiation levels in crew spaces or assess cumulative exposure. A captain might suspect a coolant leak if his men began vomiting or showed skin burns, but by then, the damage was already done. There was no way to know whether the reactor compartment was emitting 10 roentgens per hour or 1,000. No way to track how much dose each sailor had accumulated. No way to pull a man off watch before he crossed a lethal threshold. The decision to withhold dosimeters was institutional, not technical. The instruments existed, they were simply never distributed. No protocols existed for emergency reactor repair while underway. Damage control doctrine assumed surface support and dockyard access. If a coolant leak developed, if a steam generator failed, if a pump seized, the standard procedure was to surface, signal for a tug, and wait for a tender or a tow back to base. But that procedure only worked in peacetime and in friendly waters. On a strategic patrol deep in the North Atlantic or under Arctic ice, surfacing meant detection. Detection meant mission failure or worse. So the fleet modified the doctrine quietly. Submarines would attempt repairs at sea, using whatever tools and materials were aboard, with no engineering support and no prior training. Fleet standing orders required continuing the strategic patrol, even after onboard monitoring detected coolant leaks exceeding 100 roentgens per hour in machinery spaces. The justification was operational necessity and Cold War readiness. A ballistic missile submarine off-station created a gap in the deterrent. An attack submarine returning early signaled mechanical weakness to NATO intelligence. So captains were instructed to isolate the affected compartment if possible, rotate crew through shorter watches to limit individual exposure, and maintain the patrol schedule. Historical analysis of Soviet military doctrine suggests that strategic capability was prioritized over personnel safety, a calculation that came from Moscow, not from the submarine. Within 2 years, according to internal naval accounts, certain high-radiation boats began operating on shortened rotation cycles, some reportedly as brief as 45 days, though standard patrol lengths remained longer. The official reason was operational tempo. The real reason was radiation exposure. Men were accumulating doses that caused measurable blood changes, immune suppression, and chronic fatigue. Keeping them aboard for a full patrol meant losing their qualification for the next one. The shortened cycles allowed each sailor to recover somewhat between patrols, although recovery was never complete. This created a new problem: personnel attrition. Maintaining a pool of qualified reactor watchstanders became nearly impossible. Training could not keep pace with turnover, and experienced men left the submarine service as soon as their enlistment allowed. July 4th, 1961. K-19, a hotel-class ballistic missile submarine, operating submerged off the coast of Greenland. The primary coolant loop in reactor compartment 8 fails without warning. A weld ruptures, spraying pressurized radioactive water across the compartment and dropping loop pressure to 0 within minutes. The reactor scrams automatically, control rods falling into the core to stop the chain reaction. But decay heat from fission products continues generating megawatts of thermal energy with no way to remove it. The temperature inside the reactor vessel begins climbing immediately. Captain Nikolai Zatiev, standing in the control room, watches the temperature gauge swing upward and calculates that he has perhaps 90 minutes before the core sustains damage. Without coolant circulation, the core temperature climbs toward fuel cladding failure and potential steam explosion. Scram protocols reduce fission power to near 0, but decay heat remains at 6 to 7% of full thermal output. That is still more than 4 megawatts with no removal path. At 10 degrees Celsius per minute, Zatiev estimates 90 minutes to serious core damage, and perhaps 3 hours until the temperature and pressure breach the reactor vessel and the pressure hull itself. If the hull ruptures at 300 meters depth, the submarine sinks with all hands in seconds. The only alternative is surfacing, and surfacing here, in waters patrolled by NATO destroyers and surveillance aircraft, risks capture of a ballistic missile submarine and all its classified materials. Zatiev signals Moscow and reports the casualty. But clear instructions from headquarters do not come quickly. For hours, the crew remains isolated as the crisis deepens, communication difficulties leaving them largely on their own. When guidance finally arrives, the message is unambiguous. Surfacing in NATO waters is unacceptable. Attempt repair at sea. Engineering Officer Lieutenant Yuri Pobstev reviews the reactor compartment layout and the reserve cooling system. The reserve system has a separate pump and heat exchanger, but no connection to the ruptured primary loop. A bypass must be welded from the reserve line into the primary circuit. That means cutting into contaminated piping and welding under pressure while the reactor compartment atmosphere is saturated with fission products and gamma radiation. There are no remote welding tools aboard. No radiation suits beyond thin rubberized canvas. The work will be manual, and the radiation field is already lethal. Steve calls for volunteers. 8 men step forward. All are qualified reactor technicians or damage control specialists. All understand what entering that compartment means. There is no speech, no ceremony. The men organize into rotating teams, some to cut the damaged pipe, others to position and weld the bypass section, still others to pass tools and materials through the hatch. Each man will work in relays, rotating out when he can no longer stand or see clearly. The rubberized canvas suits provide protection against radioactive particles, but offer virtually no shielding from the lethal gamma rays flooding the compartment. The radiation field is estimated at over 1,000 Roentgens per hour. At that level, a lethal dose accumulates in under 10 minutes. The first man opens the hatch and steps through. A VMA reactor operates on a closed loop. Uranium fuel undergoes fission, heating the primary coolant to 300 degrees Celsius under 180 atmospheres of pressure. The pressurized water circulates through the reactor core, absorbing heat, then flows through a heat exchanger where it transfers that energy to a secondary steam loop. The steam drives turbines, which generate electricity and turn the propeller shaft. The primary loop never leaves the reactor compartment. It is sealed and highly radioactive. The secondary loop is clean steam, isolated from contamination by the heat exchanger barrier. This separation is fundamental. It keeps fission products contained while still extracting usable energy. When the primary loop ruptures, that barrier is breached, and the entire heat removal chain collapses. The control rods slam down. The chain reaction dies within seconds. Fission power? Gone. But what Zatiev and his officers were about to confront was the brutal reality of decay heat. The fuel rods they just shut down were still generating heat. 4 megawatts of it. Continuous. Unstoppable. The physics are brutal. When uranium splits, it creates fragments that keep decaying, keep releasing energy. In the first moments after shutdown, that decay heat runs at 6 to 7% of full power. For K-19's 70 megawatt reactor, that's over 4 megawatts with nowhere to go. No coolant flow means no escape route for that heat. It doesn't shut off. It only fades. Slowly. Over hours and days, as each isotope burns through its half-life. Right now, in a sealed steel vessel, the temperature is climbing. The fuel cladding is heating. And if they can't restore cooling, the core will melt. Under certain reactor conditions, core temperature can rise at roughly 10 degrees Celsius per minute with no coolant. The zirconium fuel cladding, which contains the uranium pellets and fission products, begins to fail above 1200 degrees. At that temperature, zirconium reacts with steam, releasing hydrogen gas and additional heat in an exothermic reaction. The cladding ruptures, releasing radioactive gases and particles into the reactor vessel, and, if containment is breached, into the compartment atmosphere. If the temperature continues rising unchecked, the fuel can melt, forming a molten corium mass that can burn through the reactor vessel and the hull beneath. That is the nightmare scenario. Not just a radiation leak, but a loss of the submarine itself. K-19 carries a reserve cooling system designed for emergency situations, with its own pump and heat exchanger. But the reserve system was never connected to the primary loop. The design assumption was that primary loop integrity would be maintained, and the reserve would cool auxiliary equipment or provide backup to the secondary steam system. No one anticipated a primary loop rupture requiring an improvised bypass. Popstev's solution is to cut into the ruptured primary piping downstream of the break, weld the T-junction, and connect it to the reserve pump discharge. The reserve pump can then force coolant through the reactor core, removing decay heat even though the primary loop is compromised. The engineering is sound. The execution requires welding radioactive piping in a lethal radiation field. The reactor compartment radiation field exceeds 1,000 Roentgens per hour. Human tolerance to ionizing radiation is measured in acute dose and cumulative exposure. 100 Roentgens causes radiation sickness with nausea, fatigue, and blood cell changes. 400 Roentgens is the LD50. Half of those exposed will die within 30 days without treatment. At these extreme radiation levels, workers can reach a lethal dose in a matter of minutes. The rubberized canvas suits provide almost no protection against penetrating gamma radiation, primarily serving to prevent skin contamination and extending working time by precious seconds. But according to survivors from similar incidents, vision blurs, motor control degrades, and nausea sets in rapidly under such extreme exposure. Each man must complete his welding task, pass off the torch, and exit before collapsing. There is no second chance. Popstev's team works in relays. The first man enters, cuts the contaminated pipe, and exits after 5 minutes. The second and third men enter together, position the bypass section, and hold it in place for the welder. The fourth man welds the first joint for 7 minutes before his hands begin shaking and he cannot see the puddle clearly. He passes the torch through the hatch to the fifth man, who completes the second joint in 6 minutes before vomiting into his mask. The rotation continues for 4 hours. 8 men, each entering 2 or 3 times, each accumulating between 500 and 1,500 Roentgens of total dose. By the time the final weld is completed, every man on the team has received a dose well above the LD50. At hour 4, the final weld is complete. The reserve pump is started, and coolant begins flowing through the improvised bypass into the primary loop and through the reactor core. The reactor core temperature, which had reached approximately 800 degrees Celsius, begins to decline. The core is safe from meltdown. The pressure hull is no longer at risk of rupture. The submarine's propulsion plant is crippled but stable, and Zatyevs can begin preparing for rendezvous with Soviet diesel submarines that will evacuate his crew. The engineering team has succeeded, but as Pobstev evacuates the last man from the compartment and dogs the hatch shut, he knows that success and survival are not the same thing. Every man who entered that compartment is already dying. The damage control team is evacuated to crew berthing. All 8 men begin vomiting within 20 minutes. Skin erythema, the reddening and burning of exposed skin, becomes visible within 2 hours. These are the immediate prodromal symptoms of acute radiation syndrome. The ship's medical officer has no radiation treatment capability beyond intravenous fluids and antiemetics to control nausea. There is no bone marrow transplant, no chelation therapy, no specialist consultation. Zatyevs faces an agonizing choice: surface in hostile waters and risk capture while calling for help, or remain submerged and delay medical care for his dying crew. According to available records, he chooses his men over secrecy, bringing K-19 to the surface to transmit an emergency distress signal, knowing rescue vessels are hours away, not days. Following the reactor accident, K-19 surfaces within hours to vent radioactive gases and attempt repairs. The crew's radiation exposure continues at lower levels as contaminated coolant circulates and radioactive material deposited on compartment surfaces emits gamma rays through the bulkheads. The engineering watchstanders, who must enter adjacent spaces to monitor the jury-rig system, accumulate additional dose. The damage control team's condition worsens steadily. Fever, diarrhea, weakness. The latent phase of radiation sickness is brief at these dose levels. The manifest illness phase begins within days. With his long-range antenna damaged, Zatyevs works to transmit distress signals to nearby Soviet vessels, hoping the base hospital can do what his medical officer cannot. K-19 reaches the Soviet base on July 12th, 8 days after the casualty. The damage control team is evacuated to a hospital in Moscow. The first fatalities occur on day 6 after exposure. Hemorrhagic syndrome, internal bleeding, blood and vomit and stool, bleeding from gums and mucous membranes. Bone marrow failure, the destruction of blood-forming cells by radiation, leaves the body unable to produce platelets, white blood cells, or red blood cells. Infection and bleeding become uncontrollable. According to most historical accounts, all 8 members of the immediate repair team died within 3 weeks of exposure, despite hospitalization. Official cause of death in personnel files: pneumonia and sepsis. No mention of radiation exposure. No acknowledgement of the reactor casualty. K-19 was not an isolated case. Nearly every November, Echo and Hotel-class submarine experienced primary coolant leaks, steam generator failures, or reactor compartment contamination between 1958 and 1975. Fleet records, pieced together decades later from survivor accounts and partial archives, document radiation incidents aboard at least 14 submarines. Cumulative exposure affected thousands of submariners. Some incidents were acute, like K-19. Others were chronic, with crews absorbing elevated doses over multiple patrols until blood counts dropped and immune systems failed. The same design compromises, the same inadequate shielding, the same standing orders to continue patrol regardless of radiation levels, repeated across the entire first-generation nuclear fleet. Soviet Navy medical officers assigned to submarine bases reportedly received directives mandating that radiation sickness be diagnosed as conventional illness. Flu, pneumonia, sepsis, heart failure, anything but radiation exposure. According to available records, no radiation treatment facilities were constructed at submarine bases. No specialist referrals were permitted. No family notification of radiation exposure was authorized. Acute radiation syndrome, which has a well-defined clinical presentation and progression, was systematically erased from medical records. The doctors knew what they were seeing. They wrote fiction anyway, because the alternative was believed to be court-martial, or worse. Families received no compensation, no warning that their husbands or sons had been exposed, and no understanding of the cancers and chronic illnesses that would appear years later. By the mid-1960s, Soviet submarine crews adopted the nickname Floating Chernobyl. The term circulated informally among sailors, passed from boat to boat and base to base. It was gallows humor, but it was also accurate. The submarines were inherently contaminated. The reactors were poorly shielded. The institutional culture denied the risks, and the men who operated them knew they were being exposed to dangerous levels of radiation with no protection and no acknowledgement. The nickname predated the actual Chernobyl disaster by more than 2 decades. When Reactor 4 exploded in April 1986, submariners recognized the same pattern: corner cutting on safety margins, falsified records, denial of risk, and the treatment of human exposure as an acceptable operational cost. The submarine force was the proving ground. They finally made changes. By 1970, improved shielding appeared in second-generation Soviet submarines. Radiation monitoring equipment became more widely available, though individual dose tracking remained inconsistent well into the 1970s. Engineers sought to develop safer repair methods for reactor compartment work, though many emergencies still required hazardous manual interventions. Real improvements, driven in part by the K-19 incident and the growing recognition within the engineering bureaus that the first-generation designs were unsustainable. But here's what didn't change. Standing orders to continue patrol despite radiation casualties remained in force through the 1980s. The mission still came first. They fixed the hardware. They gave crews better tools to measure the danger. And then they ordered them to keep sailing anyway. The culture of denial, the prioritization of operational targets over engineering limits, the suppression of safety warnings, all of it persisted long after the technology improved. Better shields, same orders. The Soviet Navy had learned to count the radiation. They just hadn't learned to care. They were operating death traps, and the institution that sent them to sea knew it. The sailors who called their boats floating Hiroshimas, and later, after 1986, floating Chernobyls, were right. How many Soviet submariners were exposed to dangerous radiation levels between 1958 and the end of the Cold War? The total number remains unknown. Records were incomplete, falsified, or destroyed. Survivor advocacy groups and post-Soviet investigations have documented several thousand cases, but the true figure is likely far higher. Many men develop cancers, leukemia, immune disorders, and organ damage decades after their service. Most receive no compensation and no official acknowledgement that their illnesses were service-connected. The Soviet Navy never publicly admitted the scope of the radiation exposure problem, and the Russian government has released only limited information since. The men of K-19 who survived that July day in 1961 carried the reactor with them for the rest of their lives. Not in their memories, but in their bones, their blood, their cells. The institution that sent them into those compartments knew exactly what it was asking them to do. The pattern was instantly recognizable to anyone who had served in the Soviet submarine force. Reactor design pushed beyond safe operating limits to meet performance targets. Operators ordered to conduct tests that violated safety protocols. Institutional pressure to deny problems and maintain schedules. Falsified safety records and suppressed warnings from engineers. And when disaster occurred, the same reflex to conceal, deny, and blame individuals rather than confront systemic failures. The submarine force was where that culture was forged. The men who welded K-19's reactor compartment in 1961 understood the cost of that culture long before it made headlines. They paid with their lives, and no one outside their boats ever knew. until April 26, 1986, when Reactor 4 at Chernobyl exploded, and the world finally saw it. In the years since, these vessels have been called floating Chernobyls, a term that captures what the crews themselves had recognized decades earlier, even if
they used different words.